Okay, yeah. Okay, so let me just recap then. So we started out with the two separate models for diameter and height. We saw that diameter alone was already pretty good, explained 93% using adjusted R squared. Height alone was not that great, about 33%. When we put the two of them together, the adjusted R squared went up to about 94%. But we could see this quadratic pattern in a residual plot. So that suggested we needed something quadratic, although we can't tell from that what element is missing. Is it height squared, diameter squared, or the cross product of those two? Over here, we have the model with both diameter squared, height squared, and the cross product term. And so the AIC, the BIC, and the adjusted R squared are all much better in this model. If we look at the residual plot, you can see the residual plot doesn't seem to have much of a pattern. The only slight concern on here might be that the variation perhaps increases a bit. The variation is small for the low volumes and gets bigger. But when we look at the effect tests, you will see that this shows the problem of looking at individual effect tests, because it says that the only thing that's significant here is height and diameter individually. So that seems to suggest we don't need the quadratic terms, but that's because there's a considerable overlap between these three quadratic terms. It says we basically don't need them all, right? So we clearly do need at least one of these quadratic terms, but we apparently do not need all three of them. So the one that's least useful, it appears, is height squared. So we can try again. This time we're going to try it with diameter and height and the cross product of those two. Diameter and height cross product. And we're going to add in diameter squared, which maybe is also useful. So we know that height squared is not important, at least that's compared with this one. So now if we compare this model, let me just decrease the size of this window a bit. So if we now compare this one, and let's again show the AIC and BIC. This one, the AIC and BIC are better, only marginally, but they are slightly better. So remember, we have dropped a variable here. In fact, the adjusted R squared is also slightly better. But again, you can see, although diameter and height are strongly significant, the other two terms are still not significant. So it appears that we don't need the cross product term. So we can even try one more. So let's try it with just diameter squared added in. So volume, so again, we're going to put diameter and height, and we're going to add diameter squared in here. And if we look at this one, how does this one work? So again, I'm going to add in AIC and BIC. And you can see the AIC and BIC are even better now. The adjusted R squared is about the same. It's gone down a tiny amount. But you can see now all the terms, sorry, again, let's show the effect test. All our effect test terms are now strongly significant. So we can see that we at least need diameter, height, and diameter squared in the model. So in the early statistics textbooks that use this data set, this was essentially the endpoint. The idea was the residual plot now doesn't have a quadratic pattern inside it, and this is a reasonable model. And as I would explain to my students even then, this is actually not a good model. So why is this not a good model? Well, first of all, there does appear to be some pattern that the variability is increasing as the predicted values goes up. So that's a little bit worrying. But more seriously, The issue is, how do we interpret this model? So again, if you think about it from scientific principles, how would you expect volume to depend on diameter and height? So imagine for a moment, so I don't actually know what these cherry trees look like, but you can imagine if the cherry tree was approximately a cylinder, then you would expect the volume to be proportional to diameter squared times height. And if it was a cone, again, you would expect the volume to be proportional to the diameter squared times height. So basically, and even if it's a pyramid type shape, it's the cross-sectional area times height, right? And the cross-sectional area clearly for anything that has radial symmetry is going to be diameter squared. So we do have a diameter squared term in here and height, but they're in here as additive terms. So this model really doesn't make a lot of sense. So I still remember when I was in high school, my physics teacher always said to us, if you want to know whether you've got a physics equation right, you should start by checking the units. So the units on the left-hand side must always match the units on the right-hand side. So if the units on the left-hand side are volume, then the right-hand side, the unit should also be about volume. Right? So that clearly doesn't make sense for any of these linear models that we've looked at. So what would make sense? As we said, if volume is proportional to diameter squared times height, that would suggest that we should again be doing a log transform. So the log volume would then be a constant plus twice the log of the diameter plus the log of the height. So let's just try fitting a model that is the log of the volume against log of diameter and log of height. Okay? Now, when we do this, unfortunately, we cannot compare directly the AIC and the BIC anymore with those other ones. I can calculate it, but you'll see we get minus 100 and something. So we've basically shifted the comparison of AIC and BIC once we transform Y. So we can use this to compare with other models on the log scale for volume, but we cannot compare the AIC and BIC with the original linear units. However, we can still compare adjusted R squared because adjusted R squared is unit free. And you'll notice that the adjusted R squared is indeed slightly better than any of the models we fitted on the original scale. So it's up to 97.6%. So it's not a big increase, but remember, this is now a simpler model. And if we look at the residual plot here, you'll see the residual plot looks pretty stable. There is no obvious pattern here. There's no suggestion of a need for an extra term. And the variability looks pretty stable. Right? So think about it for a minute. What does this model say? It's saying basically, as I've said, that the log of the volume is linear in the log of the diameter and the log of the height. And both of these terms are very strongly significant. Right? So that seems already quite good. However, think about the parameter estimates for a minute. As I said, if my model is correct that volume is proportional to diameter squared times height, then on the log scale, the coefficient of diameter should be around 2, and the coefficient of height should be around 1. So if we look at our parameter estimates, indeed, the coefficient for log diameter is 1.98 with a standard error of 0.07. So 2 is well inside the confidence interval for log of diameter. And log of height is a bit higher, it's 1.12, but the standard error is 0.2. So again, 1 is well within the confidence interval for the coefficient of log height. So indeed, we can even try a simpler model. So let's still use fit model to be comparable. So you'll see I have this extra term log of DDH. So that just means log of diameter times height. So I'm going to use that as my covariate for predicting log of volume. And so this one, I can now compare it not only in terms of the adjusted R squared, I can compare the AIC and BIC between these two models. So you will see the AIC and BIC are better than the one with the two covariates, because now I only have a single covariate. It's extremely significant. The adjusted R squared has even gone up marginally. And my estimate for the coefficient of log DDH is 1.005 with a standard error of 0.028. So in other words, assuming I was talking to this agricultural scientist or this forestry expert, perhaps I can go back to them and say, it's in fact very simple, that the volume of wood that you get from the tree is proportional to the diameter squared times height. And this actually tells you that the intercept on that is about minus 2.7. Remember, we're doing this on a log 10 scale. So we can easily go back and calculate what that minus 2.7 means on the original scale. That will be 10 to the power of minus 2.7. Right? So if we do the inverse back to the original scale, and so I can say this is your very simple formula, which you could then go out in the field and use, right? You can just very quickly calculate diameter squared times height, multiply it by this one number, and it will tell you approximately what volume you expect to get from that tree. And we know this is pretty good because the adjusted R squared is nearly 98%. Right, so you'll be able to quickly get an estimate. You don't even need a mobile phone to do this part. You should be able to do this part in your head. It's very simple, right? So you can see we've ended up with not only a model which is much more meaningful than the linear one, it's more precise, and it's much simpler. And it makes sense, right? It makes so much sense to say that the volume is proportional to diameter squared times height. So it's important to remember that we always should be thinking about what sort of model might make sense. Okay. So in fact, I should say, to be fair, that the more recent textbooks have gone on generally to say that you should do a log transformation. But I think, again, if your mindset is just simply in terms of diagnostics, and the diagnostic simply tells you there's a missing term, that doesn't tell you what is a meaningful model. That requires knowledge about the subject domain, right? So if I didn't tell you these variables were diameter, height, and volume, it wouldn't be obvious what is a reasonable model. So subject knowledge is almost always helpful in identifying what is a useful model. So now I want you to look at the data set called IRIS. So it's called IRIS added in the extras list. Added because I've added all these other variables, which we will look at in a minute. So the standard version of this data set is just the first 4 variables. So iris is a type of flower, and we have 3 species of iris here. So the 5th variable, species, is a nominal scale variable telling us which of the 3 species it is. And I have got colors attached to those 3 species, red, green, and blue. So that means in any plot we do, we don't even need to put labels on because we can see which species is which. And so we have these 4 measurements. So the sepal and the petal are 2 parts of the flower. So we have the length and the width of these 2 parts of the flower. So you can see the sepals are the larger parts, the petals are the smaller parts. So let's start with a graphical display. So we're going to do the scatter plot matrix, and we're going to look at the sepal and petal length and width. So we have our 4 variables. So let's increase the size of all of these. I'm going to increase it a bit more. And with the colors, you can see fairly easily here the pattern of what is going on. So you can see that, for example, the one that perhaps illustrates this the best is the petal width and length. You can see that the red species, which is the, I never remember these, the setosa, are quite distinct from the other 2 species. In other words, if I drew a horizontal line here or a vertical line here, I can completely distinguish the setosas from the other 2. And in fact, if I drew a diagonal line across here, you can see how clearly I can separate out the setosas from the other 2. But you can see also that the green and blue species, which are the versicolor and the, what's the other one called again? Virginica, are relatively hard to distinguish. So you can see there is definitely green and blue overlapping here. There's green and blue overlapping here. So in all of these plots, so the worst one perhaps is the sepal. You can see the sepal width and length is very hard to distinguish between green and blue. Petal length and sepal length is not too bad, right? We can nearly distinguish them. And again, petal length and width are not too bad. We can nearly distinguish them. So in fact, this data set, we can look at in different ways. So one way is to look at it that the measurements are the dependent variables and the species is the independent variable. The other way is to look at it in reverse. Okay, so we can either look at it as predicting the size and the size of the petal length and the petal and sepal sizes from the species, or we can say, can we predict the species from these measurements? Okay, so we can look at it in both ways. So discriminant analysis is trying to look at the measurements, saying, do the measurements distinguish between our groups? Okay, so let's have a quick look at this approach first. This goes somewhat beyond what we're going to look at. We've looked at in the class. So in this case, the species is our X and the covariates are our Ys. So if we look at this, it gives us this plot here. So this plot shows us clearly that the setosas are quite distinct. So this is essentially assuming that within species, we have normally distributed data. So this is a 4-dimensional measurement, remember? So we can't display 4 dimensions. So this is showing us a projection of the 4 dimensions into 2D space. So canonical 1 is the dimension which best distinguishes, excuse me, between species. Canonical 2 is the dimension, the second dimension, which best distinguishes between species. So you can see that the first dimension contains most of the information, right? We've got red all the way over here and green versus blue. And then these lines here are telling us how this relates back to the original 4 dimensions. So you can't see very easily on here. So let me blow this up a bit so we can actually see what is written. Otherwise, it's a bit hard to see. So if I make this fairly large, you will see that sepal length is directly in this dimension. Petal length and petal width are to some extent in this direction, but they're also in the vertical direction. Sepal width is mainly in the vertical direction. Okay, so this is telling us here, this is a test of how good our model is. This is telling us the percentage misclassified. Now we have to be a little bit careful. The percentage misclassified and the number misclassified are very low, but we're using the data set twice here. We're using the data set once to fit the model, and we're reusing the same model to evaluate it. So this is not best practice. We should be using a methodology that does not evaluate the data, evaluate the model on the same data set that we calculated on. The discriminant scores are not very interesting. That's just telling us the predicted probabilities for each individual data point. But we can ask for additional information. We can say, for example, do a stepwise selection and say, do we need all of the models? We can also look at this. So this says discriminant method. Currently, we're on linear common covariance. So that assumes that the covariance of our 4 variables is the same within each of the 3 species. So that's like saying each of these ellipses are exactly the same size and shape, right? So we're assuming that the only difference between them is the location, right? So we've got these 3 different locations, but we're assuming it's the same ellipse. We can try a model that allows for different sizes and shapes. So let's see what happens then. So the different sizes and shapes, you can see doesn't make that much difference. That again, we can see they're relatively similar. So we're not going to look at this in more detail, but let's go back to the simpler one for now. So this was our simpler one, assuming the same variance covariance for each of the 3 species. This is just more details about all of this. Oops. We can also show the group means. So this is helping us to understand how the groups are different. Where did my group means go? Oh, here we go. So this is telling us that if we compare on sepal length, you can see they're roughly 5, 6, 6.6 sepal length. Width is 3.4, 2.8, and about 3, petal length, and so on. So you can see the petal length shows a very big difference between the setosa and the other 2, and the petal width also shows a very big difference, right? And you can see that the sepal width and length, the differences don't appear to be as clear. So we could try the stepwise selection, and we can, in this case, we perhaps will put them all in first and then do backwards. So, because all in is what we were looking at just now. And you can see actually each of them were originally very strongly significant, but if we do a step backwards, so the only one it could drop out was the sepal length. So even the sepal length was significant at about 1%. So this suggests that we need the other 3. Okay, but that's actually quite a complex model in this situation. Okay, so we haven't covered discriminant analysis as such. So what I instead want to show you is something closer to what we were looking at before. This time we're going to say, can we predict the species from the 4 measurements? Okay, so this you will see JMP switches it to nominal logistic. So this is basically trying to say, can we predict which species you're in given these 4 measurements? So if we run this model, it tells us that doing it from this approach, that the petal length and width are both very strongly significant. So we definitely do need the 2 petal measurements. it's not clear which or both we need of the sepal. So the sepal length you'll see is not significant for sure. Sepal width is also not quite significant, but maybe we still need the width if we don't have the length. We can try removing the length, so we can look at this effect summary to do a quick removal. So if we remove the sepal length, you can see the sepal width is borderline. It's not that strong. So it looks like actually it might be sufficient in practice just to use the two petal measurements of length and width. Now it does say that there is some instability here to the petal length and width. Why is it unstable? It's unstable because what we have over here on this graph is what we call complete separation, right? So because we can completely distinguish this species from the other two, then actually trying to get a model that predicts membership of the red group is very hard, because there's a whole range of predictions for which this will work. So if you like, actually our predictions are too good. So that's why the real focus here is distinguishing between green and blue, right? So red is so predictable as being separable. It's really, can we distinguish the green and the blue? Now, if we look at what we've got here, you will see it's got, for the distinguishing green and blue, the petal length has a coefficient of -6 and a petal width of -10. Now, having thought about that for a moment, if we go back to the original measurements, again, we could think about these measurements in a different way. So length and width are both measurements of size, right? So we could think about it that the question is that when you've got a 2D object and I have two different measurements, what aspect of these two measurements is what really matters? So in other words, is it about the size overall of the sepal and petal, or is it about the shape of the sepal and petal? So I've actually tried to look at it that way around. So what I did to start with was just simply do a log transformation of the 4 different measurements. So let's do those two comparisons together. So let's do the scatter plot matrix on the 4 log versions and of the 4 non-log versions. So this is just the sepal length and width, but on the log scale. And let me compare that to the other one. So this was on the original scale. So the only thing I've done between these two is do a log transform. Okay? So actually, it doesn't seem to make much difference, right? It doesn't really matter very much whether we do this on the original scale or on the log scale. In fact, if I try and get these to be a little bit closer in size, you can see that it doesn't seem to make that much difference whether I do this on the original scale or the log scale. So the one in the bottom right-hand corner is perhaps the one with the biggest difference. You can see now the variability of the red ones has increased relative to green and blue, right? Because now we're looking on the log scale, so it means we're looking at relative variability. So for smaller objects, the same variability becomes larger if we look at relative variability, okay? But the real issue is the last few variables. So I've got these other 4 variables. So how have I created these? Let's have a look. So if you look at what I've done, this says, whoops, slipped off the screen. Let me just look at the formula directly. So the formula for log sepal size is log of sepal length plus log of sepal width. So that means it's the log of the area of the sepal. And the sepal shape if I look at the log of the sepal shape, the formula, you will see I put, whoops, what's going on? Log of the sepal shape, and I look at the formula. You'll see it's log of sepal length minus log of sepal width. In other words, this is the log ratio of length to width. So in other words, if this object is square, in the sense that the length and the width are the same, then the log ratio will be 0. If it's positive, that means the length is greater than the width. If it's negative, that means the length is less than the width. So if we look at, in fact, we can go back even and look at the distributions of these different variables. So let's have a look at all of these distributions so we can see what they look like. So you can see the log on the original scale is not very symmetrical, but then remember we're combining 3 different populations. And you can see that the petal length, for example, clearly has separation on both the original and on the log scale. So just the log part in that original scale is not, the log transformation is not a compelling argument simply because of distributional concerns. So the main thing is I want to understand what happens when I graph my size and shape. So does the size and shape help me to understand better what's going on in terms of my species? Okay, so let's compare this one to the previous one. So this is my one, which is just the log of the length and width, whereas this one now, I'm looking at additions and subtractions. Right, so actually, if we look at this, we can see, so this is sepal size and shape. This is petal size versus sepal size. So you can see the size one very clearly distinguishes the red and pretty good at green against blue. If I look at the 2 shape variables here, you can see that the green and blue have similar shapes, but I probably can still distinguish the red, but not quite so well. It's harder to separate the red on shape. So it appears that actually size is more useful, and in fact, that it's particularly petal size. Right, so let's have a look again. Let's try fitting my model one more time. So this time I'm going to put size and shape in here, trying to predict species. So you can see that this shows that it's the petal size that is the predominantly good way to distinguish between the species. So sepal shape has almost no value. I can remove that. And the petal shape has almost no value. I can remove that. So sepal size is a relatively weak predictor of species. The primary issue is petal size, right? So if I want to summarize how best to distinguish between the species, this is saying it's the petal size. So the length times the width of the petal contains most of the information in my data set about distinguishing between the 3 different species. Okay, so you can see it's a perfect predictor of the red species and pretty good at green against blue. So if we go back to our discriminant analysis and do the discriminant analysis using the petal size, which is what I said was good against the species, you can see indeed. So of course here now, when I look at this, you can see, again, I've got perfect separation of red, and it's almost perfect separation of green against blue. I only have 7 misclassified. So it's slightly worse than my model with 3 of the variables, but it's only slightly worse. So I've gone from a model which discriminant analysis told me I needed 3 variables down to one that only needs 1. So again, this is much simpler. Or again, I could do even discriminant analysis based on all 4 of my size and shape variables. And let's see how good my story is here. So yeah, so I've gone back to 4 misclassified here, but if I do stepwise selection, so this suggests that, again, they're all very strongly significant. So this has a much stronger assumption. So this is assuming that the distribution is normal, right? We're not sure whether that assumption is indeed valid. So that's one of the reasons why the p-values all look much stronger. So you can see, though, on this scale, again, it clearly says the sepal shape on the log scale is not useful. It still thinks all the others, though, are useful: sepal size, and petal shape. But in practice, this model is not that much better, right? So this one misclassifies 3 as opposed to 7, but this is a much more complex model. This one has 3 variables, and this one is assuming that my distributions are normally distributed and with a common covariance matrix. Okay, so it's a much stronger set of assumptions than this one, which just assumes that I have a nominal logistic distribution. Okay. Isn't the longer side always length? Yeah, so in fact, that's true. So that's why if we look at the distribution, if we look at the distribution of log sepal size and shape, you will see that the size, in fact, that's not true for the petal, but it is true for the sepal. So the sepal always has a longer length and width, but for the petal, sometimes the length is greater, sometimes the width is greater, right? So that's why we've got both positive and negative. In fact, you can arguably say that, in fact, we haven't, if we look at this, you can, let's look at it on the original scale. I can't see my colors on here, right? That's a slight problem. Yeah, let's look at petal size, log petal size by species. Right, so here you can see actually very nicely, it's basically saying that for the setosa, generally the size, oh, sorry, this is size, not shape. Yeah, for the setosas, generally the size is less than 10, sorry, less than 1. Right, yeah, so on the log scale, we've got negative values, whereas the for the other two, you can see that the log is greater than 1. So these are 10 and above. Okay, so there's quite a clear distinction on petal size, whereas the shape, yeah, the shapes for both the sepal and the petal are always positive on the log scale, meaning that lengths are greater than the width. But the fact that the length is greater than the width is not the issue. The issue is, if you like, how different they are. So it's like how elongated is the rectangle they fit in, right? Is it close to a square or not? So you can see, so for the sepal shape, 0.2 means it's fairly close to being square, whereas 1 is very different from being a square, right? So it's how squashed, if you like, your square needs to be in order to include the sepal or the petal. Okay, so let's see what next. So the next one, okay, so before we take a break, let's have a look at the bacteria one. This one is interesting because this is count data. So the one called bacteria. Now, this one, we cannot use the data set as we have been given it because, so let me explain. What this is the number of bacteria counted using 3 different counting machines at 50 different locations, okay? So location 1, we got counts of 1, 2, and 11. Location 2, we got counts of 8, 6, and 0, right? So this is count data, but it's multivariate count data. So we're not going to look at that component. We just want to try and answer the question. So the question I've written in here is there a difference in the efficiency of the 3 samples? In other words, do some of these 3 samplers or 3 observers tend to give higher counts than other ones, right? So if we just try to do a direct comparison, then that doesn't take account the location, right? So we want to control for the location as well as the observer. So we're going to assume that that these are not related. In other words, those should be separate random effects. Is the count bigger or lower because of location? Is it bigger or lower because of which observer it is? Because we do not have replicates here, we cannot do it. We cannot look for interactions. So if we had done multiple observations at each location, so if we'd done counts on 2 different occasions for each of the observers, then we could look at observer crossed with location, but here we haven't. So we need to reorganize this data in order to look at this. So how can we reorganize it? So we have these 2 options in here of stack and split. So stack says creates a new data table with values from multiple columns stacked into a single column. So that's what we want to do. So split does the reverse. Split says creates a new data table that maps several rows of one column into one row in several columns. So we want to do stack. So we want to stack our data. We want to stack 1, 2, and 3. Right? Those are the 3 observers. These are the 3 columns of counts which we want together. We want to keep the non-stacked one, which of course is the location, because we want to be able to account for location. Let's see whether I've got it right. So I now have 150 data points. So you'll see each of these is a count, so that location one here, actually I should change this from location. Sorry. The data I should change from data to count. In fact, I'm going to call it bacteria count to remind me what this is. So I have 150 bacteria counts at 50 locations and for 3 different observers. Okay, so we can now fit a model that tries to predict how the count depends on the location. In fact, I'm going to change this as well. I'm going to change label to observer to remind me. So I'm now going to fit a model. So I put bacteria count is my Y, location and observer are my X's. Now, if I just do this, JMP will assume that the bacteria count is linear data, meaning it will assume it's interval scale, and I'm assuming that the counts follow a normal distribution. But that's not true for 2 reasons. First of all, because if it's count data, the reference distribution is Poisson, not normal. And secondly, because these are integers, right? So clearly this is not continuous data. It's non-negative data. And for Poisson, we know that the variability increases with the mean. And in fact, for Poisson, the variance is equal to the mean. But in general, for count data, the variability will at least be proportional to the mean and equal to the mean if it's a Poisson distribution. So we can do this using a normal distribution just to compare and see what our results look like. So if we did that, it basically says that nothing is significant, but the observer is at least close, reasonably close to being significant, and the location is not. Well, actually, we don't really care about the location, except that we want to remove the effect of location and ask the question about the observer. So this over here tells us that the observers, the average values are roughly 4.7, 6.5, and 6.6. So it looks like maybe observer 1, the counts are less than for observer 2 and 3. Okay. Now, if this is count data, then doing a normal distribution directly on the data is a very bad idea. But what we do know is that we can approximate Poisson distribution by taking a log transform. There is a slight complication, though, because we might have some zeros. So if we look at our bacteria counts, let's have a look at the distribution. In fact, you will see that we do have some zeros, right? We have about 2 to 9% of zero. So we can't do a log transform. So in fact, what we know is that we need to make an adjustment before doing a log transform if we want to take that approach. So what we want to do is log of count. And then because it is integer, what we're going to do is count plus 0.5, because, right, if you think about it, 0 can be seen as approximately somewhere between minus 0.5 and plus 0.5. So essentially, this is interval censored data. If it really, if the true underlying distribution was normal, that means we must have rounded the answers to the nearest integer. So let's put log of count plus 0.5. So I'm going to choose bacteria count. I'm going to add 0.5. So now all my values will be strictly positive. And then I'm going to take a log to the power of 10. So this is what people used to do approximately when they had count data. Would assume, well, okay, I still want to use normal models. Then I will do this transformation. We can again then fit our model using the log of the count plus 0.5 against location and observer. So this doesn't actually change our conclusions, but this is actually a much more reasonable thing to do because the variability should be now much closer to being constant. Let me just compare that to the previous one. Oh, I closed the previous one, did I? Okay, let's compare that to the fitting the model on the original raw data. So if we look at the residual plot, you will see the original residual plot is problematic because we can see the variability increases with the mean, and we're assuming the variance is constant. On the log scale, the variance is much closer to being constant, okay? Now we've got some odd patterns in both of these because this is integer data. So the integer data means that we can't get certain points on this graph because of it being integer. Anyway, both of these are approximations to what we really should be doing. We really should be using the fact that this is Poisson. So let's try again with bacteria count, location, and observer. But this time we're not going to use standard least squares. We're going to choose generalized linear model. That means that we're assuming, first of all, that the distribution may not be normal. And secondly, that it may not be a linear model on the original scale. So generalized linear model, our distribution, we're going to start with Poisson because we know Poisson is generally usable for counts. But then it adds this thing called a link function log. What does that mean? It means that our linear model is based on the log of the mean. So for a Poisson distribution, usually we would, so the mean of the Poisson distribution must be something positive, and generally it's proportional to something. So we're saying we're fitting the log of the mean is linear in our covariates instead of the mean being linear in the covariates. So this is a sensible model for most situations where we have count data. So this is a more sophisticated model now because we have got both a distribution that's not normal distribution, and secondly, that it's some function of the mean, in our case, the log, which is linear in our parameters. Now, there are two different extra elements in here. It says over-dispersion tests and intervals and bias-adjusted estimates. So we generally want to reduce bias. Why do we want over-dispersion? Because the count data, if it's Poisson, that means the variance is equal to the mean. But quite often for count data, there is more variability than we would expect from a Poisson distribution. So we usually would at least want to check, is the Poisson distribution as such a good idea, or do we need to allow for the fact that the variance is bigger than from a Poisson distribution? So let's try that. Don't really want the parameter estimates. We want the effect test. And this says that, in fact, the observer is now significant at about 5%, just below 5%. So in other words, there is an observer effect. So the parameter estimates, most of these are not of interest. We're not really interested in the location. We're only interested in the observers. So this is, remember, we have 3 observers, so it's relative to the third observer. This says observer 1 is smaller. Observer 2 is similar to observer 3. So observer 2 is maybe slightly bigger than observer 3 on average. But the confidence interval includes 0, whereas observer 1 is different, right? So we have some evidence that observer 1 tends to give higher counts than observer 3 or indeed observer 2, okay? So, and you can see that, so, but this plot here is now a little bit different. It says the studentized deviance residual. That means instead of actually telling us the residual, so a deviance residual is basically taking into account the fact that this is not a normal distribution. It's transforming our results back to something that looks like a residual. So again, this plot should be lacking in any obvious pattern, and the variability should be approximately constant if we have a good model. So we can look at these residual plots even though we don't actually have a normal distribution. This is something comparable to the residual plot we get from a normal distribution. So you can see there are a few residuals which are a bit large here, but there doesn't seem to be any obvious pattern. Right now, of course, the problem is here that we just have these 50 locations, but we don't know anything about these locations or what their true value is. As I said, we're generally not really interested in location here. We just want to remove the location effect in order to get a more sensitive assessment of differences in the observers, okay? Yeah. So this is very useful because it means that we can actually model directly count data using what we know about count data. As I said, it's non-negative integers. It's at least approximately a Poisson distribution. Now, right, what happened to my, yeah. So, and we have here the goodness of fit test. We have an AIC. What happened to my, yeah, over dispersion parameter estimated by Pearson's chi-square. So this says that we actually have some over dispersion. Right, the over dispersion is about 3. So it means that the variability is about 3 times what we would expect if it really was Poisson data. So that's a little bit concerning, given that we have already accounted for the location. Right, so if we hadn't accounted for the location, then over dispersion would not be such a big deal, because we know that where you place the thing would explain the over dispersion. So this might suggest that maybe the measurements were taken at different times. So in other words, rather than putting the 3 observers at a location at the same time, maybe they were put there successively. So that would explain maybe why there was additional variability, right? So, so that might worry us a little bit, right? So it says that we cannot just assume Poisson distribution as it stands. We have more variability, considerably more variability, very strongly significant than we would expect if this really was a Poisson distribution. Okay, so let's take a break. It's now 10:45, so let's take a break until 11 o'clock. And then we will look at some of these remaining data sets. We're going to look at Arctic, and maybe we'll look at the US presidential one. If anybody would like me to look at any of the other ones in particular, then we can look at those. Otherwise, we'll just keep going. Okay? So let me just put the video on pause. Okay. We've got everybody here now. Okay, so the next data set I want to look at is the one called Arctic. So this illustrates a different element, which is not typically addressed in statistical packages, at least only in a limited way. So what we have here, the first four variables are the standard data set here. So this is composition, meaning we have collected the composition of samples, 39 different samples at different depths. So this would be the sort of situation where you've stuck what looks a bit like a tube, an empty tube, into the ground, and you take samples out of the ground at different depths by what gets squeezed into the tube, right? So you've got these samples, and this assumes that what we can sample only has three components, SA, Si, and Cl, which doesn't actually make sense to me in this situation because Si would be silicon and Cl would be chlorine, right? Or is it Ci? Maybe it's Ci. Anyway, we have these three components of our data at different depths, and we have reported these components. Yeah, is it Cl or Ci? I can't see clearly here. But the point is that these are components which add up to 100. So notice if we created a new column called sum, and our formula is SA plus Si plus Cl then you will see that our sum variable is approximately, at least, adds up to 100. So in some cases it goes a little bit above or a little bit below, but at least in principle this is meant to add up to 100. So there might be some rounding errors here. So it may be that, say, the fourth row, 52.2, 40.9, and 6.6, maybe it's 52.15, 40.85, and 6.55 or something like that. Sorry, the other way around, 52.25, 40.95, and 6.65 or whatever. So in other words, maybe this is just rounding error, but in principle, these are all supposed to add up to 100. So these are percentages, right? So typically, compositional data is percentages, but it could be percentages of different things. Oh yeah, sorry, you're right, sand, silt, and clay. Yes, I'd forgotten. Yeah, sand, silt, and clay makes more sense, right? So this is, sand, silt, and clay is a standard way of, so so sand is basically very fine particles, but which are still distinguishable as sand. Silt is even finer particles, and clay means that the particles are so fine it's essentially continuous, right? So clay, water will not go through at all. Silt, water goes through slowly, and sand, water will go through fast, right? So it has major consequences in terms of how well something will drain, right? So if you suddenly have a typhoon, lots of rain, if you've got clay, you're just going to get massive amounts of water left on the surface. If it's sand, the water will all disappear very quickly, and silt somewhere in between. Okay, so it's basically about the size of the particles, but it could be a chemical composition. So for example, it could be minerals, where you're looking at how much silicon dioxide you got or other chemical components. This could be time. It could be how time is divided up into different types of activity. Right? There are many different things that could be, but the crucial issue is that these are basically proportions or percentages. So if they're proportions, they should add up to 1. If they're percentages, they should add up to 100. So why is that an issue? It's an issue for a number of reasons. First of all, because we've got this constraint that they add up to 1 or to 100. So what does that mean? It actually means that there is an implicit negative correlation. So if you take the most extreme situation, if I only had 2 components, whatever one component is, the other one is 1 minus that, or 100 minus that, depending on whether it's proportions or percentages. So there must be a perfect negative correlation if I only have 2 components. If I have 3 components, there is still some implicit negative correlation because they must add up to a constant. So that means that correlations do not have an interpretable meaning if we're dealing with compositions. It also means if we have compositional data that they must all be between 0 and 100. They cannot be negative, and they cannot be bigger than 100 or 1, whatever the sum is. And in fact, the approach we're going to look at, we're going to assume that they're all positive. So we're going to ignore zeros for the moment, as we will explain why we have to do that in a minute. So the crucial issue is when we're dealing with components, what is meaningful is the ratios of these components, not their differences or their sums, right? So if you think about it, when I'm looking at proportions, so if the proportion is sand and silt, so the ratio of sand to silt is always meaningful, whereas the differences may not be. So for example, if sand is 0, then silt must, or close to 0, then that would imply that the silt cannot be less than that, right? If sand is close to 0. So differences on the original scale are not meaningful. So we need to look at ratios. And in fact, because if you think about it, do I look at sand-silt ratio or silt-sand ratio? So that's why we generally look at the log ratio. So the log ratio of sand to silt is just minus the log ratio of silt to sand. So on the log ratio scale, we can do comparisons and analysis of our data set. So so JMP actually does produce a graph that we can use for compositional data. So it has this thing strangely called a ternary plot. So a ternary plot, you see it says a 2-dimensional plot of 3 mixture components that sum to a constant. So here they talk about mixtures rather than compositions, but it's the same idea. So if we put it sand, silt, and clay in here, then this shows us the distribution of our compositions. So you will see that we do have a pattern here, but the pattern is generally not going to be linear because you've got these boundaries. You've got these 3 boundaries, right? So because of that, you're generally not going to get a linear pattern. So that's generally because what pattern there is usually on the log ratio scale, not on the original compositional scale, right? Because you can never go beyond these boundaries. So any attempt to do a linear model is doomed to failure. A, because you will get predictions outside the boundary. B, because you will not be able to account for this curvature. And C, because the variability also has problems, right? There's also going to be problems with the variability. So, as I said, what we can do is look at log ratios. So I've actually got over here different ways of looking at it. So when we've got 3 components, Obviously, there are 3 different log ratios, but we never need all 3, right? So any 2 log ratios is sufficient for us to model the 3 components. So if we have D components, we only need D minus 1 log ratios. And it's not always obvious which log ratios we could look at. So there are some more sophisticated approaches, which I don't want to go into here. But essentially, it turns out that for linear models on the log ratio scale, any D minus 1 log ratios will normally be okay. It doesn't really matter which one of them we drop, right? Obviously, you can't put 2 in there which are the same except for being reversed, but you can see. So for example, if I've got, as I've got here, I've got sand over clay and silicon over clay. So sand over silicon is just the difference of those 2. But I don't need clay over sand because that's just negative of log ratio sand over clay. And I don't need clay over silica because that's just minus of log ratio silica over clay. So I can look at how those log ratios vary. So what we have here is we have a covariate. The covariate is depth. So we could try and look to see what happens if we plot. Well, first of all, let's just do the scatter plot. We can do the scatter plot of our 2 log ratios, sand over clay versus silica over clay. So of course, that's a single plot. So this is showing us the pattern on the log ratio scale that we can see in this triangle, right? So you can see there is some sort of pattern here. There appears to be some form of a gradient, right? From one extreme, this is high sand and low silica. Over here is generally low sand and roughly equal amounts of silica and clay, right? So again, if we look at this, log ratio sand over clay, above 0 means there is more sand than clay. Below 0 means there is more clay than sand. And you'll see on this scale, we nearly always have more silica than clay. So this is, sorry, yes, almost always more silica than clay. These ones have a lot more silica than clay. These ones have roughly equal amounts of silica and clay. So this is basically showing us on another scale the same pattern we can see here inside the triangle. But in this plot here, we have removed the constraints. So we no longer have any constraints. And we can see that actually, if we look at plotting a line here, that fitting a line, well, sorry, this is on the scatter plot matrix. Let me do it in fit y by x. So if we plot log ratio sand over clay to silica over clay, let's look at this one instead. You can see it's not quite linear, but you can see there is very clearly a pattern, right? So it's a bit nonlinear. So we could fit a smoother to this. So instead of fitting the straight line, if we fit a spline, and I can adjust my spline. Let's bring this down a bit so we can see the whole thing. So if I make this spline a bit smooth, a little bit less, you can see that there is this very clear pattern, but it's not quite linear. So in other words, there does apparently appear to be some variability here, but what we don't know is how this links to depth. So what we can do now is instead fit both of these log ratios against depth to see whether we can see a pattern of how they change as the depth changes. So The first one here, again, the line is not very good. You can see this is not particularly linear. Let's again fit a smoother. I fit a smoother, you can see there is some nonlinearity here, but there does appear to be a pattern that as the depth increases, the sand to clay ratio is going down, right? So all the ones with more sand than clay are at relatively shallow depths. And as we get to the lower depths, they all have more clay than sand. And similarly, we can put the smoother on here. So similarly, if we look at silica to clay versus depth, again, you can see all the ones with very high amounts of silica relative to clay are relatively low depths. It's a rather odd pattern here. So these three don't seem to fit the same pattern as the others. Apart from these three, it seems that generally we're getting down to with equal amounts of silica and clay. So once we get to a depth of what, 50 or greater, it seems like the silica and clay become approximately the same. Okay, so that corresponds to what's going on here. So we can see that there are some data points that appear to be something of outliers, that appear to be quite a different pattern. And we can check. So if I highlight this data point here, we can see that's this one here. If I click on this one here, you can see it's this one here. If I click on this one here, you can see it's this one. So these three data points appear somewhat atypical, right? And you can see that one is this data point here, nearly at the boundary. So we can again look at the ternary plot as well. See, that one's close to this boundary. And this one here is also relatively close to the boundary. So it's these 3 points here, which don't look so odd on the ternary plot, but actually it's because the amount of sand, right, is very large in these three compared to all the rest of our data, right? Which is what makes sense up here. That's the sand clay is high. Now, we can also try using the other log ratio. So the other log ratio, which I think I've got in here as well, is of course sand to silica. So it might, even though that one is just the difference between these two, it's always possible that that one is useful. So let's also look at log ratio of sand to silica against depth. Let's see whether we can see a clearer pattern here. And in some ways, this one appears easier to understand what's going on. Again, if we fit the smoother here, you can see that generally there's nothing that looks so odd here. So it looks generally like sand to silica. We've got that the shallow ones have slightly more sand than silica. And then as the depth increases, generally, we're getting more and more silica relative to the sand. So this trend, if you like, with depth appears to be much clearer and consistent, whereas the trend for the other two doesn't appear as consistent because we've got these apparent anomalous values. So it means it's to do with you can look at it as saying it's not about sand versus silica, but it's rather how clay fits into that, okay? And in fact, although a linear model doesn't fit that well here, let's have a look to see how well the linear model fits. The linear model is quite strongly significant here, but you can see actually my nonlinear model has considerably higher R squared. So there appears to be some nonlinearity in the effect with depth. So we could try other models, of course. We could try a quadratic model with depth. Let's see how well the quadratic fits. It's pretty good, right? So you can see it looks like it's essentially a quadratic relationship with depth. Let me remove my smoothing one. So you can see that the quadratic model fits pretty well. It's explaining about 3/4 of the variability in my quadratic model. So it seems to be suggesting that sand versus silica, the ratio drops down and reaches some sort of stable level at a depth of about 60 and above. Okay, so the crucial issue here then is trying to look at on the original scale is not meaningful. So we could try plotting those. Let's look at the 3 sand, silt, and clay against depth. So as I explained, the problem with these is that actually we have these boundaries, plus we have the constraint, right? So, sorry, not what I want to do. So for example, if we look at the sand versus depth, you can see we have a hard boundary here at 0. You can't have less than 0% sand. You can't have more than 100%. And this also does not account for the constraint that the sand must be equal to 100 minus silica minus clay. Right? So yeah, we can try and fit a model here, but it will easily produce predictions which are impossible. So you can see here the linear model or the smoother are producing models which go, unless I do the smoothing right to here, then it's not too bad. But the linear model is producing predictions which are outside the boundary. So it's suggesting that when the depth is more than about 85, I get predictions of sand which are negative. So that's clearly impossible. So that's clearly a flawed model. If I look at the silica versus depth, this one doesn't seem so problematic because my predictions don't appear to be outside the bounds. But if I fit a smoother, let's get my smoother, come on. It's too much on the, running off the screen. If I fit the smoother here, you can see again, it would probably give me predictions of silica which go to negative when the depth is small, which again is impossible. And lastly, if I look at clay versus depth, then this becomes even more of a problem. You can see, well, this maybe isn't a problem in the sense that I've got a hard boundary of the depth, arguably at 0. But you can see if this suggests that when the depth is high enough, I'm going to get clay percentages above 100 in that model, which again is impossible. So if I fit my smoother again here, see if I can get my smoother here and see what happens. Yeah, so you can see once I smooth it a bit, I'm going to get predictions of clay that are negative before I get down to 0 depth. So this one doesn't become such a problem up here at high depth because it's saying that the clay is stabilizing at around 40 to 50%. Okay? Now, and as I said, correlations are also a problem. So if we look at correlations of our data, so let's look at the multivariate here. So if we looked at the first 3 variables, so it gives us our scatter plot matrix and our correlations. And you will see that of the 3 correlations, 2 of them are negative. So it says silica and clay is positive. And you can see as that's a little bit tricky because clearly that apparent linearity is true for some part of the region, but not here. But it's saying that generally the other ones are negative, right? So we can show mathematically that in any set of components that add up to 1 or 100, many of the correlations will be negative because of the constraint. right? So because they must add up to a constant, by definition, there must be some negative correlations in there, regardless of what the pattern is of variability amongst the variables. So anybody who reports correlations on proportions, frankly, doesn't understand what they're doing, because correlations, standard correlations, are not meaningful on compositional data. Okay. So what shall we look at next? So let's look at there's nobody who suggested anything. Let's look at the presidential election one. This one is interesting. So this is the one US Pres 92. Again, so let's just start with the left-hand side. So does anybody know what was special about the 1992 presidential election in the US? Anybody know? Okay, so this is too far ago, perhaps, for most of you. Most of you were pretty young in those days. So if you think about the last election, right, it was all about Trump versus Biden. So that part, at least, I assume you all followed. So in the US presidential elections, most of the time, there is only two candidates. And it turns out this has a lot to do with money, because to be part of the presidential election, you basically have to put up money in each of the states. So each of the 52 states, right, 51 states, you have to basically pay money to get on the ballot or do other things to get on the ballot. So it's actually very hard to compete in the presidential election unless you have money behind you. So they have only two major parties in the US, the Republicans and the Democrats. So unless you have either the Republican Party or the Democratic Party behind you, it's going to be very hard to participate. So in 1992, Ross Perot, who was an extremely wealthy individual, could use his own money in order to engage in the election. So he was actually on the ballot, I think, in all of the states, in all of the states in the election. So Ross Perot was able to compete, and so we actually had three participants. So that means that in Bush, Clinton, and Perot, we have percentages of the vote which they got in each of the states. And so this is, again, clearly compositional data. So most people focused entirely on Bush versus Clinton. So if we look at Bush versus Clinton, so in other words, if there was only Bush and Clinton, this is not interesting, because all the votes that Bush doesn't get, Clinton must get, okay? So you can see that there is generally a negative correlation, because a lot of the votes were competing between Bush and Clinton. But there's also Perot. So if we look at Perot's share of the vote, we look at the distribution of that, Perot's never got more than 30% of the vote. So in other words, if you think about it, that means Perot never won a single state. So the US election is a bit odd in terms of how the presidential votes work. But essentially, most of the states, all the votes go to whoever had the most votes in. So the votes in the secondary election for the president generally go to whoever gets the most votes within the state. So if I only get 30% of the votes in a state, that means I would lose out in the state's votes for president, which is, so it's essentially a two-layer electoral system. Whereas if we look at the distribution for Bush and Clinton, you'll see, so you didn't have to get 50%, right? So with a three-way split, you at least needed 33%. So you'll see Bush has a median of 38 and Clinton has a median of 43. Although in some they did poorly. So Bush only got 9% in one state and Clinton only got 26% in one state. So there are clearly states they both lost, but say Clinton has 86% maximum. Obviously, he won that. Bush had 50%. Obviously, he won that because the other 50% was split between Perot and Clinton, and Perot never got less than 4%. So we can see, that there is a pattern going on. So now again, let's look at the ternary plot for the three of them. So you can see the ternary plot looks reasonably interesting. You can see it was quite competitive, except for this one. So I've got this red dot here. So if you put your mouse over the red dot, it tells you Bush 9, Clinton 86, Perot 4. So this particular state looks completely atypical. And in fact, if you go back and look at the data set, what does it say for the state? Right? What is the 51st state on here? Anyone? Yes, it's the District of Columbia, the capital, which is not a state. So interestingly, they're actually having an argument currently in the US about whether the District of Columbia should be treated like a state, right? So when the US was originally set up as a nation, I think the compromise was that the capital should not be a state, because everybody wanted the capital to be in their state, right? The national capital. So the way they avoided that fight was by saying it's not in anybody's state, right? So they still get a vote, but obviously Washington, DC is not a state in a standard sense. It's a city, right? So cities are different from states. So although some states are quite urban, even if you take, for example, New York, we think of New York as the city, but New York is also a state, but a large part of New York's population are outside the city of New York, not just in the suburbs of New York, but there's countryside in New York State. So there are rural areas. So obviously the way people think about voting in cities is often quite different to the people who are in the rural areas. Their concerns are quite different. Okay, so we can see we have one atypical point here, one very atypical point, which is DC. So the question then is, the rest looks reasonably dense pattern here, right? So you can see that the variability other than DC is not that enormous, right? So Clinton's vote share is generally 50 to 70%. Bush's going from generally, have I got this right? 70 to 90? No, we've got this the wrong way around, have we? And Perot is small, 10 to 30%, right? So now this is a little tricky because this analysis treats effectively every state as the same. So in the real election, some states matter far more than others. So California, for example, if I remember correctly, has by far the biggest influence on the outcome because it has many more electoral votes than, say, somewhere like, what's a small one? Delaware, which is where Biden comes from, actually. So Delaware is a tiny state in terms of population. So here we're just trying to understand the pattern rather than trying to understand the outcome of the election. So the obvious thing is, is there any demographics at the state level we can use to try and understand how the vote, what makes the votes vary? Now, again, which log ratios do we want to look at? So in general, for the election, all you really care about is really Clinton versus Bush. But it is also interesting to look at Perot compared to Clinton and Bush. So there are different ways we could do it. So for example, I've got in here several different ones. I've got log ratio of Clinton to Bush, but I've also got log of Perot to Clinton plus Bush. In other words, trying to see, where are the states where Perot did well compared to the other two. right? So this is still a log ratio. And in fact, these two log ratios also characterize the whole distribution. So I don't have to choose two straight log ratios. I can look at log ratio of Clinton to Bush and Perot to Clinton plus Bush, that log ratio. Those two also enable me to go back to the original data set. So for example, we have urbanicity, meaning what proportion of that state is urban. So of course, that's in itself a composition, but I'm not going to use it as a composition here. Why not? Because DC is 100% urban. And so I can't do a log ratio of urban to non-urban, because for DC, it's not defined. So I could make an adjustment, but I'm just going to plot against urban, because I've only got a single urban variable. It doesn't really matter too much. So let's have a look at this. Let's look at, we're going to look at Clinton to Bush and Perot to Bush plus Clinton. And we're going to look at that against urbanicity. So let's blow these up a bit, not too much, because I want to do various things with it. So you can see that Clinton versus Bush, okay, when urbanicity is very high, which is DC, yes, Clinton did very well relative to Bush. But if you look at the rest, the pattern is not that strong. It does look like when urbanicity is low, that Clinton also did reasonably well, right? It's bigger than 0. So these two with relatively rural areas, Clinton did well. But for all these ones in between, it's not clear that urbanicity is very important, right? We can't see a very good pattern. What about Perot? Again, it's not really very easy to see any pattern with urbanicity. There doesn't seem to be a very clear pattern explaining, where Perot did well, where he didn't do so well. So one could argue, well, maybe that's because we have the wrong demographics here. So we only have a few demographics. So the other one we're going to look at is also proportions. This is the proportions of different ethnic groups. So again, I didn't choose these. So what we have is whites, we have blacks, we have Native Americans, we have Hispanics, we have Asians and others, right? So it's not immediately obvious what we're looking at. So again, let's for the moment just ignore the compositional nature. Let's just plot those two variables again. So again, we're going to look at Clinton versus Bush and Perot versus the combination of the two. Let's just plot that against each of these ethnicity variables to see whether we can get some idea about how we might want to look at this. So if you look at this, so if we look at white, you can see white doesn't seem to make too much difference for Clinton versus Bush. Black also doesn't seem to be that important. Native American, Hispanic. So you'll notice that actually DC has a lot of blacks, doesn't have that many Hispanics, doesn't have many Native Americans, doesn't have that many Asians. So the main thing about DC is it's not only very urban, but it's also very black. So it's a far higher proportion of black than any of the other states that we're looking at. However, when we look at Perot, you can see not much of a pattern against white, but a strong pattern against black. What else can we see here? We can see some apparent pattern of Perot for Asians, right? So Perot did poorly when there weren't many Asians. But then also we have one state with very high levels of Asians. Does anybody know which state in America has lots of Asians and others? So to be fair, it's Asians and others, but I think it is actually largely Asians. Anybody know which state has a majority of people with Asian ethnicity? No? It's Hawaii. Yes, Nicholas got it right. It's Hawaii, right? So many people in Hawaii are ethnically Japanese. So in fact, I was just watching a Netflix documentary on the Second World War. It's one of these ones where they've taken the Second World War TV coverage and colored it, which makes it much more interesting to watch. And they were talking about Pearl Harbor, which basically started the Second World War for the Americans. So they were talking about before the Japanese bombed Pearl Harbor, in fact, the Americans were worried primarily not about getting hit by air because they didn't think that was very possible. They were actually worried about sabotage by the people of Japanese origin who lived in Hawaii, which turned out not to be the case. So there was a saboteur on Hawaii, but he was actually he had Japanese nationality, not just Japanese ethnicity. So the Japanese people who were ethnically Japanese were generally locked up in America during Second World War, even though there was, I think, very little evidence that they were disloyal, if you like, to America. So they generally did not support the Japanese in the war, in the Second World War. Anyway, so you can see that the one that looked most interesting was black. So maybe we will look at a black variable just to try and see what that's going. As I said, we can't look at black on its own. So I'm going to look at the log ratio of black over white. So log ratio of black over white clearly is meaningful. So let's have a look. Let's plot both of those. So how well did Clinton do versus Bush, and how well did Perot do compared to the pair of them against log of black versus white? So as I said, surprisingly, it doesn't seem to make that much difference for Bush versus Clinton on the face of it. But if you look at it here, maybe that's not quite right. So you can see it does appear that there is some evidence, although that's probably biased by DC. So we could, perhaps just to be sure that DC does not have too much influence, we can exclude DC. So we'll click on that row. We're going to hide and exclude DC. Well, we won't hide it. We're just going to exclude DC for now. That means that in our analysis, it will not be calculated in. So let's now look at Clinton versus Bush and Perot versus the pair of them. Log black versus white. So now we have excluded DC. So can we see any pattern for Clinton versus Bush? It is sort of, it's not significant. If I choose the smoother now, so now I no longer have being biased upwards by Washington, you can see doesn't appear to be much pattern at all. So this is a little surprising on the face of it, because the belief was that although Clinton and Bush were both white, Clinton had for a long time been a senator in a southern state, but it doesn't seem to have helped him very much. So unlike when Obama was standing, because Obama was partially black, a lot of blacks went out to vote for him. So it looks like the blacks didn't particularly turn out for Clinton. That's not particularly, but if we look at Perot, you know, the effect on Perot, we can see generally it's a very large effect. And if we put the smoother on here, you can see it's even pretty extreme, right? So basically, so let's see, yeah, so there are never more, once we've taken DC away, there are never more blacks than whites. But if we look at the states where, relatively speaking, there are more blacks than whites compared to other states. So if you look at this half here, you can see generally Perot did very poorly. So the only ones where he didn't do particularly poorly are the ones with very few blacks, right? So as soon as there are more blacks in the election, then Perot does very poorly relative to Clinton and Bush. Okay, so this is a sort of analysis that we can do. Now, what else? Yeah, there's nothing else in this data set alone, as I said. We could look more carefully at the Hispanics and the Asians plus others. Again, we would need to put in some log ratios in order for this to be meaningful. Okay? Now, we've still got, actually, I think maybe I should stop there and go back to the assignment. So, because you all have the data set now, but I want to go through again what I'm expecting from you in the report. So I don't want to talk about these general issues here. I want to talk about specifically the findings, analysis, and result, and the conclusions. So as I've said in the main body of the report for this report, so I don't expect you to have written much in the other parts. Obviously, in the introduction, you need to explain something about where the data comes from and what the variables mean in your data set. But we don't need a lot of details, but at least to have some idea about what are the key research questions. Now, the findings and analysis, I've said there are at least 4 things which must be in there. So I want you to at least have to explain what was the best model that you found. And that not just say this is the best model, but why do you think that is the best model? And that means you need to, in the 4, compare it with other models. So presumably there would often be some simpler and some more complex models. So why is it better than the simpler ones, and why is it better than the more complex ones? Yes, no, there is no minimum of A4 pages as such. But I think, frankly, it would be very hard for it to be, what did I put as the maximum here? I think I wrote down a maximum excluding the appendices, right? 6 pages. So I think generally it's hard for it to be less than 2 pages because you need to have answered all 4 of these points, and you need some tables of comparison. So the summary of other models you examine means there must be at least 1 table, and the summary of diagnostics means there must at least be a couple of diagnostic plots. So those would generally take up probably 1 or 2 pages already. And then there should be at least another page of explanation as to why that model is the best one, right? So generally somewhere around 3 or 4 pages is probably enough, but definitely not more than 6. So you need to develop the skill of being concise. You need to have enough information to justify your conclusions, but you also don't want to present large amounts of information which is not very relevant. So the summary of other models, I don't really want to share a sample report because it depends on the data set you've got and the sorts of models you're considering, right? I've already given you some very explicit guidance here about what I expect. So we have gone through a large number of different diagnostics. So obviously you would need some residual plots. You probably would need a leverage plot as well to illustrate whether there are any problems with high or low leverage points. The residual plots, we talked about both the pattern of the residuals and whether there are any particular residuals which are particularly high, right? These are the sorts of things that you need to be considering. Okay, and then the conclusions should link back to the terms of reference and the discussion, those 4 discussion areas that we've just mentioned. Okay, and in the conclusions, you should reference any limitations. So for example, If in your diagnostic plot you found out that none of your models fit that well, or that which, regardless of what analysis you do, there are always some large residuals, then that's something that you should discuss as a limitation. You might, for example, compare the analysis with any extreme data points removed and see whether it affects your conclusion. If it does not affect your conclusion, then obviously those data points are not that important and it doesn't matter too much whether you include them. But if your conclusions change radically after removing potential outliers, then that means that you need to consider the possibility that those either could be truly outliers or they could just be very important data points, but where the experimental design of this study did not collect data which was sufficient in order for us to say definitively what is a good model for this data set. Okay? So you remember we looked at, when we were looking at some of those data sets, you remember that in the RO data set, we saw that one data point was extremely influential, but it looks like that data point is actually very important. So there's a weakness in the way the data were collected. So obviously, I'm assuming in most of these cases, you did not collect the data, or even if you did, you didn't come up with the experimental design. So you may not be able to do anything about data that was not collected in a very consistent manner across the different possibilities. So clearly that would mean not only a limitation, but perhaps a recommendation that there is a need to collect some more data, right? So you need to draw on the lessons that you have got from going through these previous data sets. Again, as I hope you've understood, one of the key issues is what is a meaningful model for this data set, right? So if it's a compositional data, then you need to account for the fact that it's a composition. If it's count data, you need to account for the fact that the variability increases with the mean. If the variability is not constant, which is our standard assumption, you should be thinking about transformations, right? So these are all the things that you should be focusing on, that you have hopefully learned from following along with the data sets we've analyzed in class. Okay? Any other questions? So let me just put this in here, right? So no minimum hard to be less than 3 pages, right? I mean, it depends to some extent on how simple the story is with your data set. Sometimes it's very clear which data set is the best. In other cases, it may be more challenging to identify which model is the best. Now, if when you get to the analysis phase, you discover that there is no interesting model at all for your data set, you can always come back to me and discuss changing the data set. I think from looking at the data sets you've all sent me, you should be able to find a reasonable model for all the data sets you've shown me. Obviously, some have much higher adjusted R-squared than others, but even a model that doesn't have a high adjusted R-squared may still be a useful and meaningful model, right? It sort of depends on the context, what the sorts of research questions are, and how much inherent variability there is in the way that the data were collected. Okay? So as I mentioned at the beginning, I have sent another email to JMP asking whether they will let me have an extended license. I will hopefully get an answer on Monday. And if so, then I will send that out to everyone. If you have any questions about the assignment, you're welcome to email me and I will try and respond promptly. Okay? As I said, normally I'm rather relaxed about the submission date, But as I retire from Hong Kong U at the end of June, although I think, so Hong Kong U has now got rather ridiculous. In theory, I may lose my email address after 1 month, although I expect to have an honorary appointment, so that won't happen. But sometimes these things take time. So it's really in your own best interest to sort out and finish the assignment within the next month, as originally proposed. So please do not try not to let it drag on beyond the middle of June, as I'll be busy entering my office and everything else at that time. Okay? If it really is a problem in finishing, then I will give you another email address to contact me, but I prefer to try and finish everything up neatly before I retire. Okay? Any other questions? Thank you very much. And I wish you all the best with your studies in Hong Kong U. Okay?